Excellent. Okay. Yeah, so today I would like to showcase how we can use the combination of in situ and remote sensing data that is available from Solar Orbiter to study one specific aspect of solar activity, and that is particle acceleration and transport. And I'm giving this talk basically on behalf of a joint working group of 6 of Solar Orbiter's instruments. And you will immediately see that this is very much a team effort. We all know that our sun is the most energetic particle accelerator in the solar system. We know from remote sensing observations that ions and electrons are accelerated in the solar corona and precipitate onto the sun in the framework of solar flares. Here we see one example where we can see a flare in EUV and hard X-rays. But we also know that particles can leave the sun and propagate through interplanetary space, through the heliosphere. And this snowstorm you see here are actually highly energetic particles that have been accelerated by a coronal shock wave. In this talk, I want to focus on one specific aspect, and these are the so-called solar energetic electrons. Why are we focusing on electrons? Well, electrons have the advantage that we have much better constraints on them from the remote sensing side on the sun, because they are readily detectable in hard X-rays and in radio. For ions, we can only do that with gamma rays, and these observations are quite limited. However, still that the observational situation is better on the electrons, there are still many, many open questions. We do not really understand fully how the particles, the electrons are accelerated, by which mechanism. We do not understand their timing very well. We do not understand how these spectra work. So there's a lot of things that still have to be understood. And our goal is to use Solar Orbiter's unique capabilities to further our understanding on the solar energetic electrons. As you know, the goal of the whole mission is to link the sun to the heliosphere. In our case, to link the remote sensing observations of particle acceleration at the sun to the in situ particles that are detected at the spacecraft. And Solar Orbiter is unique in 2 ways. On the one hand, it combines the remote sensing and the in situ observations on a single spacecraft with a very comprehensive set of 10 instruments. And on the other hand, we sample different locations in the inner heliosphere. So we are times at 1 AU, and sometimes we are really close to the sun. Later in the mission, we will move out of the eclipse. Coming back to the instruments, what are we really doing when we want to study solar energetic electrons? Well, it all has to start with the energetic particle detector, which gives us the in situ observations of the electrons. Then we go back to the sun and look into hard X-rays with the STIX telescope, which is sensitive to energies, electrons of energies of the same range that EPD can detect. We complement that with the extreme ultraviolet imager, which gives us context information on the flare or the eruption that is associated with the event. What happens on the sun and what arrives at the spacecraft can be partially linked by radio data from the RPW instrument, because this provides us a sort of a tracing of energetic electrons as they propagate through the upper corona and inner heliosphere. But not only flares are potential accelerators of these electrons, also CMEs might play a role, and therefore we also use the coronagraph METIS and the wide-angle heliospheric imager Solo High to look for any associated CMEs. And finally, the particles need to travel through interplanetary space and reach the spacecraft, so we need to characterize the conditions in interplanetary space. For that, we need data on the solar wind from SWA, and also on the interplanetary magnetic field from MAG. Basically, we're using 8 of Solar Orbiter's 10 instruments. To do this work, a joint working group was founded that started off as a STIX EPD effort, but since it has grown and now includes also RPW, EUI, METIS, and Solar High. And our goal is to compile a comprehensive event catalog of all solar energetic electron events that were recorded by EPD, and also the associated or potentially associated solar events. And secondly, of course, we want to use this data to conduct statistical studies of these events. And to do that, here are listed all our collaborators. And you see this is a large number because this is really a huge effort. And all the instrument teams are really putting in a lot of work here. Let us start with the detection of the solar energetic electrons. This is, of course, done with the energetic particle detector, EPD. So here you see count rates at different energies. EPD covers the range from 2 kV to 80 MeV with different sub-instruments. Here we see that electrons are arriving. We see peaks in the count rates. But EPD can also constrain the anisotropy of the events, or the EPT sub-instrument can do that because it has different look directions, which you see here. And here you see that only in one channel, the one which is looking to the sun, we have an increase. So this is really a highly collimated particle beam, therefore a large anisotropy. Lastly, we can also measure the composition of any associated ions with the cis instrument. With the electron events, we usually also see ion enhancements. Here's an example from cis. And the advantage of cis is that it also works as a mass spectrometer, so we can get some indication on the species of the ions. And here we have an event where we see enhanced helium-3. And that is very peculiar, and it defines basically a certain event category. These are the so-called impulsive events. They are highly enriched in helium-3 and in iron. And usually this is associated with acceleration connected to magnetic reconnection, as we see it in solar flares. In contrast, there are the so-called gradual events, where we see no significant elemental enhancements. And this is more consistent with the acceleration of the particles at shock waves. And in the remainder of the talk, we will see that those two event categories really make a difference and will show peculiarities in several different aspects. When we want to associate events on the sun with the particles that arrive at the spacecraft, of course, we need to know when those particles were launched at the sun. We use EPD for that, and we are employing two different techniques. The most basic one is the time shift analysis, where you just have you use one single energy channel. You know the energy of the electron, for example, therefore you know its speed, and then you need to assume a path length. We take the Parker spiral length, and then you get an injection time on the sun. Of course, it's not said that this is the true path length, because that is certainly an idealization. Therefore, if possible, we do the velocity dispersion analysis. There is a significant number of events where we see that the energetic electrons arrive earlier than lower energy electrons. This is a spectrogram from EPD plotted as inverse speed. So high energy particles are down here, low energy electrons up here. And you see the high energy ones are arriving first. If we assume that all of those electrons are injected at the same time at the sun, we can fit this and obtain a solar release time or injection time. And in addition, we get the constraint on the path length. So we are no longer, the assumption of a Parker spiral is no longer required. And this is basically the more accurate method. Then we look, do we see a solar flare in the time interval? For that, we primarily use STIX, the X-ray telescope. With STIX, we can do imaging spectroscopy in hard X-rays from 4 to 150 keV. This covers both the thermal plasma that is heated by the electrons at the sun and the energetic electrons themselves. And this is the same energy range that is also covered by EPD. So we can look into the same particle population. From STIX, we get quick look light curves, and this we use to associate the events. We also get the spectrograms, which we then can later fit to get more quantitative information on the energetic electrons. And we can also reconstruct X-ray images. So we see where actually the sources are. So in this case, we see 2 foot points. These are the regions where non-thermal electrons rain down into the deeper atmosphere and generate X-rays. Concerning radio, we look into radio spectra from the RPW instrument. So here is a dynamic radio spectrum. Time runs here On the x-axis, on the y-axis, we have decreasing frequency. So this is plasma emission, so emission at the local plasma frequency or its harmonic. And those fast drifting structures you see here, drifting from high to low frequencies, are signatures of electron beams that generate Langmuir turbulence and then generate radio emission. So we know that during those times, electrons are accelerated in the corona and moving out into interplanetary space. These are the so-called type 3 bursts. And there is also a different type of radio burst, the type 2 burst, which would be more slowly drifting. And they are signatures of shock waves, which are also candidates for particle acceleration. So what we do is just to associate the inferred injection times with our X-ray flares and radio bursts. And this is a textbook example. So here we have the time shift analysis onset time determined from EPD and this more refined VDA onset time with the velocity dispersion analysis. They are quite in good agreement. And in this case, there's one Styx flare and one type 3 burst, which is very close in time to our inferred injection time. So this is really a textbook example that we would immediately associate both the radio burst and the X-ray flare to this electron event. Of course, there are events where it's not that clear cut, but this is in general the idea. Then we also look into EUV, into full disk images from the EUI telescope, which gives us both chromospheric and coronal coverage. We search for associated EUV events and identify eruption types if we see an eruption. So in this case, if you see here, we have some jets which are moving out here. Those are events which are often associated with electron events. And we note down also the location of this event and the active region which is associated. Looking farther out in the corona, we use METIS to constrain any associated CMEs, and farther out, the solar high heliospheric imager. This gives us the association with CMEs, and we also measure some of their parameters like speed, width, and also the launch time. Finally, what we have to do is to establish the magnetic connection of the spacecraft, because the particles, these are charged particles, electrons, they are tied to magnetic field lines, they have to follow them. So it would be very informative to know which place on the sun solar orbiter is connected to. And for that, we use the magnetic connectivity tool developed by our colleagues at IRAP. Basically, we have a photospheric magnetogram. You make a potential field source surface extrapolation up to a distance of about 2.5 solar radii, at which point the magnetic field lines become radial, and then connect to that the nominal Parker spirals. And then you get your connection from the spacecraft to the source surface and then to your foot point. In that case, solar orbiter was connected probably to this active region here. And in the end, we couldn't put everything together. This is now for this same event. We have a full disk EUV image. We have the two sources from Styx and from EUI, which are consistent. We have this connectivity foot point, which still connects to the same active region. So given all the uncertainties with this modeling, this is still a quite good agreement. And in that case, we also saw a CME that was associated with this event. So in this case, everything fits together quite nicely. Finally, we also look into the interplanetary context. So what are the conditions in the interplanetary medium? For this, we use SWA and MAC. We basically need solar wind parameters like the solar wind speed to get the Parker spiral for the time shift analysis. And we also use the magnetic field structure to identify any complex structure. So are we in the quiet solar wind, or are we within an ICME, a flux rope? Are we near a stream interaction region or the heliospheric current sheet? Because that will certainly influence particle propagation. In the end, what we want to come up with is a comprehensive catalog. This is now called the Comprehensive Solar Energetic Electron Event Catalog, or COSECAT. So COSECAT is near completion. We will release this soon. We're just finishing up the paper that describes the contents of the paper of the catalog and the first statistical results. And once that is published, this will be all be open to the community. At the moment, COSICAT contains 303 EPD solar energetic electron events. This goes from 2020, so from the beginning of the mission till the end of 22. We also have additional events during the next few years, but the analysis has not been finished. So in total, we have over 600 events now. Here is the monthly event rate we see. You see that this is increasing. This is consistent with the increasing solar activity. Here for comparison is the number of STIX flares that are observed per month. Also increasing, but there's not really very one-to-one correlation between them. And this is the changing distance from the sun. So in this period, we've covered about 4 orbits. Here are some basic statistics. So we've spoken about these impulsive and gradual events in terms of composition. Most of our events are impulsive, 3/4 of them. The rest is gradual. This is the anisotropy distribution. So the anisotropy is large, meaning it's really beamed-like for many events, or at least medium, and only in a tiny fraction of events the anisotropy is small. That means those events where probably scattering plays a very large role. And in those events, we would think it's quite difficult to associate solar events with in situ events. But this shows that for most cases, this is actually not the case, and the association should be rather okay. Association with flares is also quite large. So with STIX flares, nearly 90% we find associated STIX flares. Also with EUI events, in most cases, we see an association either just with a flare or with a flare and an eruption. The unknown fraction here is larger due to the duty cycle of EUI. But there are also a few events where we don't see any STIX counterpart. So it will be interesting to look into these, what's special with those events. In terms of flare size, here is the GOES class, or I should say the GOES equivalent, since we only have GOES measurements for about half the events. Because on the other times we're behind the sun with solar orbiter. So we use STIX to generate a GOES equivalent. So this ranges from B-class flares up to X-class flares. The smaller the flare class, the more events, which is typically seen with solar flares. So we divide this distribution by the distribution of all flares that have been observed with STIX during the same time interval. And then we get the fraction of flares that do show an solar electron event. And this shows you that for B-class flares, the association is about 1%, and then it rises. And for M and X-class flares, it's 10% or even more of those flares also show an SEE event. These are some results on the source positions and the magnetic connectivity. These are the source positions in helioprojective coordinates rescaled to 1 AU. So you see that the events are coming from the 2 activity bands since they're associated with active regions. And in blue, we see the impulsive events, in red, the gradual events. And here it's immediately evident that the blue events, the impulsive ones, are clustered on the Western hemisphere, which is to be expected since due to the curvature of the Parker spiral, solar orbiter is mostly connected to the Western hemisphere. We can look into that in more detail and compare the source location we see here with the location of this foot point of magnetic connectivity we determined earlier on. And this here gives you the latitude difference between the STIX source and the connectivity foot point, and here we see the longitude difference. Again, we see that the impulsive events are strongly peaked around 0, so they tend to really tend to occur close to the foot point of magnetic connectivity. Whereas the impulsive events, if you look down here, show much flatter distribution. Sorry, the gradual events. So this shows you that for gradual events, it doesn't really matter that much where on the sun they are occurring. And this means that the acceleration region probably has to be quite extended. So this would confirm this picture, which we have since a longer time, that gradual events are probably due to acceleration at CME-driven coronal shock waves, which are extended, whereas the impulsive events are more associated with the more confined or more localized reconnection events that are going on in the framework of solar flares. Some further statistics, CMEs with METIS, we only see it in about 20% of the events, but this association actually gets higher if we just look for the gradual events. So another confirmation of this CME-related origin of those events. And finally, the type 3 radio bursts. Indeed, in most cases, we do see type 3 radio bursts, either a single one, multiple ones, or even type 3 storms, so many of them going on. And indeed, we would expect that since these are really features that trace electrons that propagate outward from the sun. And the last point I want to show here of our ongoing investigation is the time difference between the electron injection at the sun and the solar events. So here I've plotted histograms of the injection time, here with the more basic time shift analysis, and the peak of the STIX X-ray flare. So if this time here is negative, it means that the injection at the sun happens before the flare peak. And if it's positive here, it means that the injection is delayed. And what we find is that in most cases, the injection is indeed delayed. And that has been known for some time. That is one of the unsolved questions. Why is the injection usually delayed? For impulsive events, we find that it's more clustered towards small injection time delays with a median of about 5 minutes or so. Gradual events, again, much more flatter distribution, and there are also outliers at very long delay times of several hours. With velocity dispersion analysis, which is with a more refined method, we see basically a similar trend. The distribution is even narrower. We don't have those outliers, but again, the impulsive events are significantly better associated in time with the flare than the gradual events, which could again mean that the gradual events are actually not flare related. So studies like these have been performed before, but now what we can do with Solar Orbiter for the first time is to look into those time delays as a function of distance from the sun, since we're sampling those events between 0.3 and 1 AU. And this plot here shows you, the scatter plot shows you these injection time delays with the more refined velocity dispersion method versus heliocentric distance. And again, I've split it into impulsive events in blue and gradual events in red. If we first look at the gradual events, we see that there's no correlation with distance whatsoever, quite some large scattering. If we look into the impulsive events, this changes a little bit. We begin to see a weak trend of an increasing injection time delay with distance from the sun. The correlation coefficient is rather low, but it is a first tentative hint. But what we can do now, what we've done here actually is apply some filtering. We split it into impulsive and gradual events. And now we can continue to do some filtering since we still have a decent number of events and filter for different parameters. And I want to show you one example. This is now only for the impulsive events. On the left here, again, for the main hard X-ray peak. On the right here for the type 3 burst onset. Basically, you see the same trend. And here I filtered for simple interplanetary conditions. So this means that we are in more or less well-behaved, Parker-like, quiet interplanetary conditions. And we've removed the more complex scenarios. And if we compare those two, this is all events, and this is now just the simple configuration ones. You see that the correlation has significantly improved, and several of those outliers have been removed. And now we find rather decent correlations, and we still see both for the radio burst and the X-ray flares that there is an increase of this injection time delay with distance. And this would mean that the injection time delay we usually observe at 1 AU is at least partly due to propagation effects that accumulate the farther away we are from the sun. Whereas when we're close to the sun, the delays are actually much smaller. So as a summary, I hope I could show you that Solar Orbiter really provides us with unique capabilities, particularly to study particle acceleration and transport in the heliosphere. It gives us the first opportunity to separate acceleration from propagation effects, as I've just showed. And one of the results of this first statistical analysis is that we really see strong support for the flare-related origin of impulsive solar energetic electron events. Our next steps, as I already mentioned, is to publish the COSY catalog together with the first statistical results. Our intention is, of course, to keep COSY-CAT updated as the mission progresses. So we are always adding new events to it, and we are continuing with the analysis of new events. And there will be data releases in the future, which then cover a larger fraction of Solar Orbiter's mission. A very important next step will be to perform a spectral analysis with STIX and EPD to get a better handle on the spectral shape of the energetic electrons, both at the sun and in interplanetary space, and also study this relation as a function of distance from the sun, because we want to see if there are also effects that change the spectral shape as the particles propagate away from the sun. And finally, of course, what I've shown you is just using data from Solar Orbiter plus some ground-based magnetograms. Of course, we also are keen to include in situ electron or particle observations in general from other locations in the heliosphere. Luckily, at the moment, we have several other observational assets that are active in the heliosphere. And we are, of course, looking forward to further collaborations with other teams. And our catalog should be or is intended as really a starting point to foster such future collaborations. Thank you very much for your attention.
Thank you so much. I'm going to stop the recording.